Dear students, in this lecture we discuss line integrals. So you are familiar with the integral of function on an interval. In this chapter we discuss integrals on a curve. Okay, instead, so here uh, the path of integral will be a curve instead of just just interval. Okay, so we discussed integral of the form, say integral from a to b f of t dt. Okay. For f from interval ab to r. In this chapter, we generalize this integral. So the interval AB is replaced by a curve in Rn. Okay, let us see some basics. Path and line integrals. Okay, so we discussed the definition of path and then we define line integrals. So first we discuss path or a curve. Definition. Let alpha from interval AB, closed interval AB to Rn be a vector valued function okay, values are in Rn means it is vector valued function. Okay, defined on a finite closed interval AB, defined on a finite closed interval. We call it as capital Z, Z equal to closed interval A. So if we consider a point T in this closed interval AB, then we get image of this T as alpha of T in Rn. Okay, so as T moves in this interval AB, it traces out a curve in Rn. Okay, as T runs through J, the function values alpha of t trace out a set of points in Rm called the graph of alpha, called the graph of function alpha. Okay, so graph of alpha is equal to set of all points alpha of t in Rn such that t belongs to interval A. If alpha is continuous on Z, this graph is called a curve. If alpha is continuous on interval Z, then this graph is called a curve described by alpha. Let us see example of such curve or path. Example. Consider alpha 1 from closed interval 0 to pi to R2 defined by alpha 1 of t equal to, okay, so values are in R2, so it will be a vector in R2 given by ordered pair. So it is sin t cos t. We define another function alpha 2 from the same interval to R2 defined by alpha 2 of t equal to cos t sin t, and third function alpha 3 from 0 pi closed interval 0 pi to R2 defined by alpha 3 of t equal to, it is a vector whose components are sine of 2t cos of 2. Okay. Then all these functions alpha 1, alpha 2 and alpha 3 will trace a curve in R2. It is nothing but a circle centered at origin and radius equal to 1. Okay, you can check. So if the components are x of t and y of t, then here you can see x of t square plus y of t square is sin square t plus cos square t, and that is equal to 1. Okay, so alpha 1 of t traces a circle in R2 centered at origin, radius equal to 1. Same thing is true for alpha 2 and alpha. Okay, then alpha 1, alpha 2 and alpha 3 trace, it is also called as unit circle. Okay, the circle in R2 centered at origin and with radius 1. Okay, but there is difference. However, so we have some observations. First thing is orientation. So about alpha 1 and alpha 2, we can see that orientation of alpha 1 and alpha 2 is different. Okay. For example, if we put t equal to 0, then point on alpha 1 t is sine 0 cos 0, that is 0 1. Okay, so x is 0 and y is 1. Okay, so this is first point. If we put t equal to pi by 2, then we get sine pi by 2 cos pi by 2, that is 1 0. Okay, so x is 1, y is 0. Okay, so this is the next point. So okay, so we can realize that the curve traced by alpha 1 is clockwise. On the other hand, if we consider alpha 2, then the things are exactly opposite. Okay, because the components are interchanged. Okay, so when t is 0, then we get 1 comma 0, that is x is 1, y is 0, this point. And when t is pi by 2, then we get cos pi by 2 sin pi by 2, that is 0 1, x is 0, y is 1. Okay, so this is second point, for example. Okay, so we can realize that the same circle is traced by alpha 2, but it is anti-clockwise. Okay, so orientation of alpha 1 is different from alpha 2. Okay, what about third? Let me write this. Whatever. First thing, orientation of alpha 1 is clockwise, whereas the orientation of alpha 2 is anti-clockwise. So we can have different orientations. Or different directions. Next thing, we can compare alpha 1 and alpha 3. Orientation is same. Okay, as you can see, orientation of alpha 3 is also clockwise. However, speed of alpha 3 is double as compared with alpha 1, because let us see. Okay, so when we are at t equal to 0, we are having same points for alpha 1 and alpha 3, that is 0. Okay, so at t equal to 0, it is 0 1. Okay, so this one, x is 0, y is 1, same initial point. Now when we are at pi by 2, alpha 1 is at this point 1 0. Okay, on x-axis, positive x-axis. However, alpha 3 of pi by 2, it is sine 2 into pi by 2, that is sine pi, that is 0, and here cos pi, that is minus 1. Okay, so instead of this point, we are at 0 minus 1, means at negative y-axis. Okay, so when alpha 1 is at this point, alpha 3 is at this point, means speed, this velocity of alpha 3 is double as compared with this. Okay, okay, so velocity is vector, speed is its absolute value. Okay, so we can see right as a speed of and velocity vector is given by alpha 1 dash. Okay, so alpha 1 dash of t is velocity vector of alpha 1, and its absolute value norm. Okay, usual norm in R2, Euclidean norm. So norm of x order pair x comma y is square root of x square plus y square. Okay, so you can check here speed of alpha 1 and speed of alpha 3. Okay, and realize that speed of alpha 1 is 1 and here it is 2. Okay. Speed of alpha 3 is double than that of alpha 1. Okay, even though the orientation is same. Okay. Next definition. Let J equal to closed interval AB be a finite closed interval in R. A function alpha from J to Rn, which is continuous on J, is called a continuous path in Rn. Alpha is smooth if alpha dash derivative alpha dash exists and is continuous on if the derivative alpha dash exists and is continuous on open interval AB. This path is called piecewise smooth. Piecewise smooth if the interval AB can be partitioned into a finite number of subintervals in each of which the path is smooth. In each of these subintervals, the path is smooth. Yes, alpha dash exists and continues. Okay. So how such path will look like? For example, the following figure shows a piecewise smooth path. Okay. So it can be traced like this. Okay, so this path, this piece is smooth, then next we have like this. Okay, so note that at this point, the curve is not smooth. Okay, that means here the derivative does not exist. Okay, so this curve is continuous, but derivative at this point doesn't exist. Okay, so this cannot be smooth curve, but it is piecewise smooth. Okay, if we make two pieces of this curve, then this first piece is smooth, second piece is also smooth. Okay, like this we can have more than one pieces. Okay, so this is piecewise smooth path. So all these basics were required for the definition of line integral. Let us define the line integral. Definition of line integral. Let alpha be a piecewise smooth path so there is domain say closed interval AB and values are in Rn. So let alpha from AB to interval AB to Rn be a piecewise smooth path and let F be a vector field defined and bounded on the graph of alpha. F be a vector field. So it is vector valued function. Okay, so its values are in Rn. Vector field defined and bounded on the graph of alpha. Okay, we know that graph of alpha means collection of all the points of the form alpha of t, where t is in this interval AB. Okay, so alpha of t is in Rn. So here domain of F is subset of Rn. Okay, and that should contain all these points alpha of t. So on these points, this F should be defined and bounded. Okay, so we can restrict the domain of F to all such points alpha of t. That is graph of alpha, trace of that curve. The line integral of f along this curve alpha, the line integral of this vector field f along alpha is denoted by integral f dot d alpha. F dot is dot product, okay? D alpha. We are going to see how to define this, and is defined by the equation and is defined by the equation integral f dot d alpha equal to integral from a to b f of alpha of t dot alpha dash of t dt. Okay, so note that the integral on right hand side is usual integral. Okay, integral of function defined on interval a b. Okay, so f of alpha of t is in the domain of f. Okay, so f is from Rn to Rn, it is vector field. Okay, so f of alpha of t, this is vector dot product with alpha dash of t. So alpha dash of t is component wise derivative. So if our alpha is this one sin t cos t, then derivative of alpha is derivative of sin of t comma derivative of cos of t. That is equal to cos of t comma minus sin of t. Okay? And this is usual dot product of two vectors. Whenever the integral on the right side exists, whenever the integral on right side of this equation exists. Okay. Now we see some other notations, some more basic things, and then we solve example. Okay. So other notations for line integrals. If capital C denotes the graph of alpha, means it is collection of all the points of the form alpha of t, where t is in the domain of alpha, denotes the graph of alpha, then the line integral integral f dot d alpha is also written as integral over this path C f dot d alpha, and is called integral of f along C, and is called integral of f along C. Next, if the vector a bar is nothing but alpha of initial point in that interval A. Okay, so our domain of alpha is interval AB. So if initial point is a vector A bar and vector B bar is alpha at point B. Okay, so this small a is the real number, this A bar is vector. Okay. Same is true for B bar and B. Denote the endpoints of C. So these are endpoints of that curves. This path C, capital C. The line integral is sometimes written as the line integral can be written as integral from A bar to B bar of f or integral from A bar to B bar of f dot d alpha. Okay. And this is line integral of f from A bar to B bar along alpha. When A bar equal to B bar, then this path is said to be closed. Okay, like a circle as we discussed. Okay, so these paths are closed paths. If A bar equal to B bar, that means alpha of A is same as alpha of B, then alpha is closed path. In this case, we denote, in this case, we use this symbol integral over closed path for the integral over closed path. Next thing, so representation of line integral in terms of components. In terms of components. Okay, so components of f, components of alpha, etc. Okay. If alpha and f are expressed in terms of components, say alpha equal to alpha 1, alpha 2, and so on, alpha n. Okay, so in our example, the components of this curve are sin t cos t. Okay, so for second it is cos t sin t. Okay, these are component functions. And components of f equal to components f1, f2, and so on fn. Then the integral, then the integral integral on right side of this definition. That means this integral from a to b f of alpha of t alpha dash t dt. So let us see. It is integral from a to b f of alpha of t dot alpha dash of t dt equal to integral from a to b. What is f of alpha of t? It is vector f1 of alpha of t, comma f2 of alpha of t, and so on, fn of alpha of t. Okay, this is f of alpha of t dot product with vector alpha dash t. Alpha dash t is, its components are alpha 1 dash of t, alpha 2 dash of t, and so on, alpha n dash of t. Okay. Now dot product of two vectors. It is component wise multiplication and then sum. Okay. So it is integral from a to b. It is summation k is from 1 to n. That is f1 alpha of t multiplied by alpha 1 dash of t plus f2 of alpha of t multiplied by alpha 2 dash t plus and so on. Last term is plus fn of alpha of t multiplied by alpha n dash t. So in general, we can have summation k equal to 1 to n f k of alpha of t multiplied by alpha k dash of t. Note that all alpha k dash of t are real numbers. Similarly, fk of alpha of t are also real numbers. So this is product d. Now this is finite sum, so we can write this as summation of integral of these things. Okay, so it is sum k equal to 1 to n integral from a to b fk of alpha of t multiplied by alpha k dash of t. Okay, so we take integral of all these things and take summation. If our alpha is in R2, okay, in a plane, in the two-dimensional case, if alpha is from AB to R2, then alpha can be described by using parametric equations. X equal to alpha 1 of t and y equal to alpha 2 of t. Okay, so these are parameters of alpha. Okay. Therefore, this integral over C means trace of alpha, f dot d alpha. This line integral is nothing but integral f of alpha of t dot alpha dash t dt is from a to b. And now we can realize that f of alpha of t means f of x comma y. Okay, it is f1 of xy comma f2 of xy, and alpha dash means it is dx and dy. Okay, dx by dt and dy by dt. Okay, so let me write. This is integral from a to b. Components of f of alpha t are f1 of xy, comma f2 of xy dot. So what is alpha dash of t? It is dx by dt, comma dy by dt. Okay, so dx by dt, it will be dx and this will be dy, and so we just have integral from a to b f1 of xy multiplied by dx plus f2 of xy multiplied by dy. Okay, so these are differentials dx dy. Okay. So similarly, we can have in R3, if our curve alpha is from AB to R3, then our components will be x equal to alpha 1 of t, y equal to alpha of t, alpha 2 of t, and z equal to alpha 3 of t. Similarly, our components of f will be f1, f2, and f3. And this thing will be f1 of xyz dx plus f2 of xyz dy plus f3 of xyz dz. Okay, so it will be in R. Next time we solve some examples based on this formula, line integral. Thank you.